Neptune, the eighth planet from our Sun, is a world of mystery and dynamism. It is an ice giant, composed primarily of heavier elements than hydrogen and helium. Its distance from Earth makes it difficult to study, but what we have learned is captivating. Neptune's atmosphere is a swirling canvas of storms and clouds, driven by powerful forces we are only beginning to understand. The blue color of Neptune is striking. This is not the blue of water as on Earth. It is the blue of methane gas, which absorbs red light and reflects blue. The presence of methane, along with other gases like hydrogen and helium, gives Neptune its distinctive hue. These gases form a thick atmosphere, constantly churning with activity. Neptune is a place of extremes. It is incredibly cold, with temperatures plummeting to hundreds of degrees below 0 Fahrenheit. Its winds are the fastest in the solar system, reaching supersonic speeds that dwarf even the most powerful hurricanes on Earth. These winds whip around the planet, creating a dynamic and ever-changing atmosphere. Our understanding of Neptune is constantly evolving. Each new observation reveals more about this distant world. From its swirling storms to its icy composition, Neptune continues to fascinate and inspire scientists and space enthusiasts alike. Its secrets beckon us to explore further, to unravel the mysteries of this enigmatic giant. Neptune's atmosphere is a complex and dynamic system. It is composed primarily of hydrogen and helium, similar to the gas giants Jupiter and Saturn. However, Neptune also possesses a significant amount of methane. This methane is what gives Neptune its distinctive blue color. Methane absorbs red light from the sun and reflects blue light back into space. This is why Neptune appears so brilliantly blue in images. The deeper blue color of Neptune, compared to Uranus, is due to the presence of an unknown component that also absorbs red light. The atmosphere of Neptune is not uniform. It is divided into bands of different latitudes, each with its own unique characteristics. These bands are characterized by variations in temperature, pressure, and cloud composition. The interaction of these bands creates the complex and ever-changing patterns we observe in Neptune's atmosphere. The study of Neptune's atmosphere provides valuable insights into the nature of gas giants. By understanding the processes that drive Neptune's atmospheric dynamics, we can gain a deeper understanding of the atmospheres of other gas giants in our solar system and beyond. Neptune is home to the fastest winds in the solar system. These winds can reach speeds of over 1,200 miles per hour, more than twice the speed of sound. To put this into perspective, the strongest hurricanes on Earth rarely exceed 200 miles per hour. The exact cause of these extreme winds is still a subject of scientific study. However, it is believed that Neptune's internal heat plays a significant role. Unlike Earth, which receives most of its heat from the sun, Neptune generates a significant amount of heat from its interior. This heat rises to the surface and drives the powerful atmospheric currents. These winds are not limited to a specific region of Neptune. They whip around the entire planet, creating a swirling vortex of activity. The interaction of these winds with the various atmospheric bands creates the complex and dynamic patterns we observe. The study of Neptune's winds provides valuable insights into the dynamics of planetary atmospheres. By understanding the forces that drive these extreme winds, we can gain a deeper understanding of the processes that shape the atmospheres of other planets, both within our solar system and beyond. One of the most striking features observed on Neptune is the Great Dark Spot. This massive storm system was first observed by the Voyager 2 spacecraft in 1989. It was an oval-shaped storm, similar in size to Earth, with winds raging at over 700 miles per hour. The Great Dark Spot was a dynamic feature, constantly changing shape and intensity. It was not a permanent fixture in Neptune's atmosphere. When the Hubble Space Telescope observed Neptune in 1994, the Great Dark Spot had vanished. This highlighted the transient nature of Neptune's atmospheric features. The exact mechanisms that drive the formation and dissipation of features like the Great Dark Spot are not fully understood. However, it is believed that they are related to the complex interplay of Neptune's internal heat, atmospheric composition, and powerful winds. The study of the Great Dark Spot and other similar features provides valuable insights into the dynamics of planetary atmospheres. By understanding the processes that lead to the formation and dissipation of these storms, we can gain a deeper understanding of the complex interplay of forces that shape the atmospheres of other planets. Neptune's atmosphere is not just a swirling mass of gas. It also contains a variety of clouds composed of different chemical compounds. One of the most prominent cloud types is composed of methane ice. These clouds form in the upper layers of Neptune's atmosphere, where temperatures are cold enough for methane to freeze. Methane ice clouds are visually striking. They appear as bright white features against the deep blue of Neptune's atmosphere. These clouds are not static. They are constantly forming, dissipating, and moving with the powerful winds that whip around the planet. The distribution of methane ice clouds is not uniform across Neptune's atmosphere. They are more prevalent in the southern hemisphere, where temperatures are slightly colder. This difference in temperature is thought to be related to Neptune's axial tilt, which causes the southern hemisphere to receive less sunlight during part of its orbit. The study of Neptune's methane ice clouds provides valuable insights into the atmospheric processes of gas giants. By understanding the factors that influence the formation and distribution of these clouds, we can gain a deeper understanding of the complex dynamics of planetary atmospheres. Neptune radiates more heat than it receives from the Sun. This internal heat source is a key driver of Neptune's dynamic atmosphere. The heat originates from the planet's core and slowly makes its way to the surface, where it interacts with the atmosphere. The exact mechanisms that generate this internal heat are not fully understood. However, it is believed to be related to the gravitational contraction of the planet and the radioactive decay of elements in its core. This internal heat source is a defining characteristic of gas giants, distinguishing them from rocky planets like Earth. The interaction of this internal heat with Neptune's atmosphere is what drives its powerful winds and creates the complex and dynamic patterns we observe. The heat creates convection currents, similar to those that drive weather patterns on Earth, but on a much larger and more powerful scale. The study of Neptune's internal heat source and its impact on the planet's atmosphere provides valuable insights into the evolution and dynamics of gas giants. By understanding these processes, we can gain a deeper understanding of the formation and evolution of planetary systems. Continued observations of Neptune, building on the legacy of Voyager 2, are crucial to unlocking the secrets of this distant, dynamic world.